Hi guys, welcome back to my channel. So today we're going to be looking at integration by parts, and we can almost think of this as like a reverse product rule, where we're dealing with the product of two functions, u and the derivative of v. And what I would actually suggest doing, there's another YouTuber called Nancy Pye. She is fantastic. She does a wonderful video on this, and most of the information from her video I've actually used in this little introductory video here. So go and check her out if I sort of muddle my way through this, because she explains it very clearly, very well. Okay, so let's do this. Let's use an example here. So we've got an integral of x cos x dx. So we're multiplying two functions by the other. And one of these we're going to let equal to u, and one of these we're going to let equal to the derivative of v. And sometimes it's really doesn't matter, to be honest, which one we define as u and v. And sometimes it's really, really important to have specific functions that are given to u and specific functions that are given to v. So here's a little tip for choosing u and v. So since this value here, u at the front, we're saying that this is a function. And then when we get to this answer here, we're going to have to find the derivative of that function. So we want to pick something that's going to be easier to derive. And quite often it's more important that we pick u first. So we really need to know which one u is going to be. And the v will sort of just follow from that. So we're going to pick something that's easier to derive, because that's what we're going to have to do. Now, conversely, with this derivative of v, we're going to have to integrate it to get these two values here. So we want to pick something that's not going to be harder to integrate. Okay, so we've got a nice little acronym here, and that acronym is LIATE. And this is the order by which you should be picking functions for u. So if you pick a log functions are kind of crazy, and when you derive them, they become more simple. Same thing with the inverse trig functions. When you derive them, they become more simple. Algebraic functions, when I'm talking about algebraic functions, if I had something like x squared, if I was going to derive that function, that's going to be equal to 2x. Similarly, if I was going to integrate that function, that would have x to the power of 3 over 3. And it's pretty easy to derive, but it's starting to get more complicated when we integrate it. So depending on the other types of functions in there, this could be better off as the derived function, or it could be better off as the integral function. So really, we need to be careful when we're considering which ones we pick. Last two on the list here, trig functions, they get trickier as we derive them. So we would sort of put them towards the end. And then same thing with exponential functions. So like 10 to the power of x, they become more complicated as we derive them. So we don't want to use them for our u function. Okay, so let's go ahead then. So this x here, this is an algebraic term. And then cos x, that is going to be a trig term. Okay, so it's pretty easy to see that this value for x is going to be my u, and therefore cos x is going to be my function, my derivative function here, v. So I'm going to rewrite these, and I'm going to say let x equal to u. And so the derivative with respect to x, actually let's write this using this same notation, so the u dash v that I've written up here. So the derivative of this is going to be equal to 1. Okay, so now we can write the derivative of v, which is going to be equal to cos x. And remember, we've chosen the derivative of v because of our LIATE acronym here. And so now we are going to have to integrate this function. So we're going to pick something that's not going to be harder to integrate. And so v is going to be equal to sine x. And we're going to ignore the c because that will come at the end of this integral system here. So now that we've got that information, we can substitute those values in. So if I rewrite this from scratch, the integral of x cos x dx, where x is my u and cos x is my derivative of v, is going to be equal to u times by v. So in other words, x times by sine x minus the integral of v, which is sine x, times by u, and luckily, the derivative of u, and luckily the derivative of u is 1, so we just have to integrate sine x. Nice simple one. So then this is going to be equal to x sine x, and then when we integrate sine, we get negative cos, negative and negative make positive cos x, and then we'll add our c there at the end. So that's all we have to do to integrate by parts. So let's use another example now. And I've just written my little acronym LIATE along the side here. So this term here, x squared, that's an algebraic term. E to the power of an x, that is a exponential term. So we would pick this to be our v dash function, or our derivative of v, and we're going to pick x squared to be our u function. So let's just write that formula from before. So if we have an integral of the form u times by the derivative of v, that's going to be equal to u times by v minus the integral of v times by the derivative of u. Okay, excuse me, I'm losing my voice a little bit. So let's rewrite this so that u is equal to x squared, and so therefore the derivative of u is going to be equal to 2x. Now our derivative function, so v dash, was equal to e to the power of x, and notice how this one is going to be really easy to integrate. So that's why I like to make sure that we follow this LIATE structure here. So then when I integrate this, I'm just going to get e to the power of x. Nice and simple. All right, so let's substitute into our equation now. So when we have an integral of the form u multiplied by the derivative of v with respect to dx, that's going to be equal to u times by v, so x squared times by e to the x, minus the integral of v, which is e to the x, times by the derivative of u, which is 2x. All right, so as we can sort of see here, this is still a little bit complicated. So what we might have to do is we might have to do some further integration by parts. So what I'm going to do, we're just going to ignore this part of the equation for now. We're just going to focus on finding the integral of this. So let's pop that just in the middle here. And so this is going to be a new function here. So we've got e to the x multiplied by 2 to the x. And so that's going to be equal to our new integral of u times by the derivative of v. And so now we've got a new u v minus the derivative of v u dash. And this is why we want to pick something that's going to be easier, or sorry, that's not going to be harder to integrate, because we're going to have to integrate it a second time. And so that's why we have to be really careful with the functions we pick for u and v. I think I've said that enough now. I'll stop saying it. Okay, so in this case, we've got an exponential function. So this is going to be our derivative of v, and then 2x is an algebraic term. So this is going to be our u function, because we always want to choose. This is how we are going to choose our u value. So we're going to choose that first. So let u equal 2x, and so the derivative of u is going to be equal to 2. Our derivative of v is equal to e to the x, and so therefore our function for v is going to be equal to e to the x. And again, we're going to add the constant at the end. So let's just finish substituting these values into this original expression. So the integral of e to the x to x, remember 2x is my u and e to the x is my derivative of v in this case, is going to be equal to u times by v. So in other words, 2x times by e to the power of x minus the integral of v, what was v? E to the x times by prime u, and that is going to be 2. And that's going to be with respect to x. Okay, so this is going to be pretty simple to integrate now, because when you integrate an exponential function, it's just going to be another exponential function. So we get 2x e to the x minus 2 lots of e to the x, and then plus c, but we'll do that again at the end. So now that we have this information, we can substitute it back in for here. So we get that the integral of this function is going to be equal to x squared e to the x minus everything that's in this brackets here. So that's going to be minus 2x e to the x plus 2e to the x, and now we'll add that constant on the end there. So I just went ahead and quickly checked that answer in the textbook, and that is our correct solution. Alrighty guys, I might come back in the next video with some more complex familiar type examples of integration by parts, and if you haven't already, go check out this video by Nancy Pye, because she does an awesome job. Alright, thanks guys, I'll see you in the next video.